Okay, now we're going to look at a something called a transshipment problem, and this is not hard at all. A transshipment problem is simply a transportation problem uh, with some intermediary nodes. So, for example, if you're shipping from, let's say, Alaska, California, and Texas, and you ship from those, let's say, factories, and you go through a couple of different warehouses, maybe uh, Chicago, maybe St. Louis, and then you go to different destinations on the East Coast. Perhaps that's New York and that's Florida. And you can have as many different nodes as you want, but this is enough to illustrate what a transshipment problem is. It's pretty simple in that it's just like the transportation problem. So let's say each of these nodes has a particular capacity or supply, and each of these ultimate destinations have a particular demand. So let's say it's 200 and 100. And then similar to the transportation problem, there's a cost associated with getting one unit from any particular origin node to these what are called mediating nodes or transshipment nodes. Okay, so now before going to New York or Florida, I've got to go through Chicago or St. Louis. So let's label these nodes. I'm going to go 1, 2, 3, 4, 5, 6, 7. I didn't label those 1, 2, 3, 1, 2, 1, 2 because it would create some duplicate decision variables. Um, and then from these transshipment nodes, you can move on to the ultimate destination. And then there's a cost associated with shipping one unit on any of these arcs. Okay, so let's say it costs $2 to ship one unit from node 1, Alaska, I guess, to Chicago. Node 4, $3, $3, $4, $5, $1. And then we have costs associated with getting from the transshipment nodes to the ultimate destinations. Let's say $2, $4, $4, $6. Okay, so the goal once again is to minimize total transportation costs. So again, you'd have the objective function that looks like this: 2 minimize 2 times x 1 4 plus 3 times x 1 5 plus, I'm not going to write all of these, but you'll have a decision variable like this for each arc, and the last will be plus 6 x 5 7. So once again, xij corresponds to the number of units shipped from a particular origin to a particular destination. You'll have the same constraints you had in the transshipment or the transportation problem, rather, in that you have three supply constraints. You have a constraint here, a constraint here, and a constraint here that just exactly like the transportation problem, you can't ship more than 100 units out of origin 1. So that'll look like this: x 1 4 plus x 1 5 must be less than or equal to 100. And you'll have the same constraint for node 2, x2 4 plus x2 5 less than or equal to 100, x3 4 plus x3 5 less than or equal to 100. So I can't ship more than I have. Those are my supply constraints. And then similarly, I have these destination constraints, these demand constraints that say I have to receive 200 units at node 6 and I have to receive 100 units at node 7. So you could probably say x4 6 plus x5 6, which again represents collectively how many units get to node 6. And that has to be greater than or equal to 200. I have to receive what is needed. And you'll have another destination constraint here. x4 7 plus x5 7 must be greater than or equal to 100. Now in the middle, we've got to have what are called transshipment constraints. Now, this is a constraint that imposes reality on my potential solution space. And that reality is if it didn't arrive there, it can't leave there. So unless it arrived at node 4, it cannot be shipped from node 4. Another way to think of this is what goes in must equal what comes out. And that's generally how I teach it. I'll tell students, just remember what goes in equals what comes out. So let's look at what goes into node 4, and you'll see that x1, x14 plus x24 plus x34 represents everything going into node 4. So if it goes in, it has to leave. So that there has to equal x46 plus x47. You'll have one more constraint just like that for your transshipment node 5. x15 plus x25 plus x35 equals x56 plus x57. What goes in equals what comes out. And you've just formulated another transshipment problem. Just like a transportation problem, only we added some pretty simple constraints. What goes in equals what comes out. Might be more logical to say what comes out must equal what went in. In other words, we can't just invent stuff to ship from nodes 4 and 5. It has to have arrived there. Okay, that's all for the transshipment problem.